Hi, and welcome to 4.5 Newton's Third Law. In this lesson, students will be able to describe Newton's third law and apply it to everyday interactions. So I like to start off by thinking about this. How does a rocket propel itself through space? It's not pushing off anything, so what the heck is going on? How is that even possible? I don't know, let's find out. Newton's third law. If two objects interact, the magnitude of the force exerted on object 1 by object 2 is equal to the magnitude of the force simultaneously exerted on object 2 by object 1, and these two forces are opposite in direction. In other words, for every action, there is an equal and opposite reaction. Because the forces coexist, either force can be called the action or the reaction. They happen at the same time, so they're simultaneous. Now, it's easy to say, okay, action, reaction, I got it. But then when you go to do your free body diagram, you have two vectors, two force vectors that are look like they're canceling each other out because you have an action pointing to the right and then the reaction's pointing to the left. So don't they cancel each other out? How can you possibly ever get a net force if there's all these action-reaction pairs? Well, it's important to remember. So action-reaction pairs do not imply that the net force on either object is zero. In other words, the action-reaction pairs do not cancel each other out. It's important to remember that there are two separate objects being analyzed. So you cannot just draw a box and like our free body diagram and be like, okay, action and then reaction. How many objects do you have right here? Only one. No, you need to, it's a object exerting a force on another separate object, and then you do those free body diagrams separately. Now you might have a force, and that, so F1, and then on your other one, okay, that's the same magnitude, but in opposite in direction, and now we're ready to analyze the rest of these forces separately. The action-reaction forces are equal and opposite, but either object may still have a net force on it. So I always like to, at this point, I would walk over to the front of the classroom and open the door and say, how was I able to open the door? And, you know, then there'll be a bear on the other side of the door. No, I'm just kidding. So there, the bear is opening the door. Why don't the forces cancel out? Well, we have to analyze these separately. So let's say that the door is being opened to the left by the bear, just like we drew before, and the bear is over here. Maybe I should try to draw a bear. Look at that nice bear. Okay, so the door is being pulled open by the bear. And guess what? The bear feels the door. Right? It's not like if you're going to open a door, it's not like you can't feel the door. You're exerting a force on the door, and the door is exerting a force back on you. You could feel it. I'll draw it on his hand. You could feel the door with your hand. So if you pull harder on the door, you're like kind of digging your hand into the door more. You could feel more pressure on your hand. The harder you pull on the door, the more force you will feel at the same exact time. It's simultaneous. It's simultaneous. It's an equal and opposite reaction. And why don't these cancel each other out? Because they're two separate objects. So the bear also is standing on the ground, and we didn't talk about frictional forces yet, but there's a frictional force between the bear's feet and the ground that is compensating for the force that you feel with your hands, right? It's not like you go sliding around. If this was ice, maybe if it was icy, he would be harder to get a foothold, and he might like make himself fall over. But yeah, if it's a good amount of friction there, you could get some traction. You're not going to go anywhere. However, doors are specifically designed so that there's minimal friction. They have hinges. All right, and if it's a well-oiled hinge without squeaking too much, All right, just a little bit of a tug on the door. Maybe there's a little friction. Maybe it's a heavy door. Who knows? But that amount of frictional force should be, if it's a good door, easily overcome by the amount of force that you're pulling. So, yes, it's equal and opposite force, but they're two separate objects that you have to think about differently. And they don't just cancel each other out. It's easy to overthink it or underthink it and think that they cancel each other out. That's a common misconception that you'll run into. So I'd just like to do a few more examples. If you're sitting at a table right now, you can push yourself out from the table if you're, especially if you're in a wheelie chair. All right, so as you push on the table, you're pushing on the table this way, okay? And the table doesn't move because this is your applied force. There's a frictional force on the table. Well, you feel this applied force on your hands, and it's an equal and opposite reaction. And the frictional force between your chair and the ground is less than the frictional force between the table and the ground, presumably. So this applied force beats the smaller frictional force, and it's enough to push you backward. The same magnitude, opposite direction applied force is felt by the table, but there's more friction there, so it balances out. So I'm just giving more examples of Newton's third law, so hopefully it sinks in. Same thing, bat hits ball, ball hits bat. If you swing and a miss, you're not going to feel any resistance, right? But when you hit that ball, you feel something happening. You feel the resistance. So the bat is exerting a force on the ball. Boom. Okay. I don't know why they're erasing. And the ball is exerting a force on the bat. An equal and opposite. This is the force that you feel. Okay. Well, why does the ball go flying off and you and the bat don't? It's because you're holding on to the bat and your body is in contact with the ground and you have a frictional force between your feet and the ground. So it would take more force. You would need a lot more force in order to make you go flying backward or the bat go flying backward, the same amount that the ball goes flying forward. So it's an equal force, and you feel it. If you get a nice hit, sometimes you feel the sting in your hands. You can feel this force, but it's not enough to make you go flying. The ball feels the force, and the only other force acting on it is gravity and a little bit of air resistance. But this large force makes it go flying into projectile motion. Oh, I put an A over here, FG, because I was thinking about air. Okay, another example. So we have a helicopter hovering in the air. Now we're talking about thrust, and it's kind of like the same concept with the rocket from the beginning, the critical thinking. So what's happening here? For the helicopter, the blades are actually pushing the air downward. And you could see that if you see people walking out from underneath, you see all the wind pushing downward on them. Well, the equal and opposite reaction is that the helicopter feels a thrust upward. So the air is being pushed down. The air is the object, one of the objects, and the helicopter is being pushed up. All right, another example of thrust. We have a balloon, and I would blow up the balloon, and then you let it go around the classroom, and it's crazy, right? So again, the air is being pushed out this way, and in reaction, the balloon is being pushed to the right. So on this slide, we have Mario jumping up in the air. So what's happening here? Earth is exerting a force on Mario downward, Fg. Well, Mario also exerts his own gravitational force. We didn't talk about like what causes gravity yet, but basically, if you have mass, you have a gravitational field around you. So Mario has mass, and he does exert a gravitational force upward on the Earth. FG, it's equal and opposite. Well, the result of that is apparent with what happens with Mario. Mario's gonna just go up and then come straight back down because Earth's pulling down on him. Um, but why doesn't the Earth come shooting up towards Mario? Because Mario is its own separate object. So the acceleration of Mario is equal to the force divided by Mario's mass. Well, you could have the same force. We'll make it like this: the force is the same, but what is the mass of Earth? The mass of Earth is huge compared to the mass of Mario. So even though it's feeling a force, Mario's pulling upward on the Earth, but the Earth's mass is so huge. What happens to this fraction if you have a very large denominator? The acceleration of the Earth is so small that it's negligible. Even if you took every person that is living on the Earth, you brought them into one spot and they all jumped up at the same time, it would still be negligible because that is how, think about it, it's the mass of the Earth. That is a large amount of mass, a large amount of inertia. So you would need a large amount of force in order to move that Earth. There is a force being felt there. It's equal and opposite to the force that Mario feels, but it's not enough to accelerate the Earth. And Mario's mass is super tiny, so we see that acceleration. So this is an example of how the regents might test your knowledge on Newton's third law. And remember, think of it in context of the big end of your test. You're answering questions from all over the place. So the answer to this might seem apparent right now because we're talking about Newton's third law, but after doing a bunch of different concepts, you might get tripped up by this. So let's read it together. It says a student pulls a 60 Newton sled with a force having a magnitude of 20 newtons. So let's just say that the 60 Newton sled is saying that the weight of the sled, Fg, is equal to 60 newtons. And it says a student pulls on the sled with a force of 20 newtons. So they're pulling on the sled with an applied force of 20 newtons. So that's the situation there. What is the magnitude of the force that the sled exerts on the student? And you might think to yourself, oh, do I add these two numbers together? Do I subtract them? Is it the 60? Is it the 20? Do you know the answer? It's going to be the 20 newtons, okay? And here's why. The student is pulling with 20 newtons, and he feels or they feel that resistance. The sled pulls backward on them with 20 newtons as well. All right. The sled is on snow and there's less friction there. So this 20 Newton force is enough to cause the sled to move forward. The resistance is felt, right? The student might not be running as fast as they would otherwise. They feel the resistance of the sled, but there's more traction between them, their feet and the ground, so they're able to continue going forward. These two forces aren't canceling each other out. They're acting on different objects. So really it's a force being felt on the sled with a smaller frictional force, and the student feels the same magnitude. All right, it's the same magnitude as this force over here, but they're also pushing themselves forward. There's traction between their feet and the ground. So overall, they get to accelerate forward, and overall, so does the sled. So that's, again, just explaining how they don't cancel each other out. But the thing to look for in this particular problem says a student pulls on a sled with a force. What is the force that the sled pulls on the student? So they'll do that switcheroo on you. The student pulls on the sled, and then the force that the sled exerts on the student. So equal and opposite reaction. That's kind of how they'll set it up. And I've seen this question asked a bunch of different ways, but it kind of always says the thing exerts a force on the other thing. What's the force that the other thing exerts on the first thing? Back to the definition, object one and object two. So I'll leave you with this. Another critical thinking: you are stuck in the ocean with a sailboat and no wind. So just hanging out there. You do, however, have a huge fan. Can you propel your boat through the water? And in the classroom, we have this setup with the fan and it's blowing air towards the sail. So does it work like a sailboat? What will happen? Okay, so think about it and then watch this video. I'll put this in the extension video folder, and you can check out what happens. That's a Mythbuster episode. And that's about it. Thanks for watching and have a great day.